So I chose to do my presentation on genetic algorithms. First, a little bit about the history. The genetic algorithm was first developed by John Holland. It started in 1962 with his work on adaptive systems, and then in 1975, he published Adaptation in Natural and Artificial Systems. In the 80s, there was a rise in popularity, and then in 1992, Koza used genetic algorithms in his method, genetic programming. So what are genetic algorithms? A genetic algorithm is pretty much a randomized search algorithm developed to imitate natural selection in genetics. So at each time step, the GA selects random individuals from a fixed population to serve as parents, which will produce the next generation. Over these generations, the population evolves, optimizing the solution. This approach is ideal for discontinuous, non-differentiable, stochastic, or highly nonlinear problems. So there are 5 main components of a genetic algorithm. The first is to initialize the population. The GA initializes the population of candidate solutions through random selection, with each individual being a solution to the problem being solved. These candidate solutions are known as chromosomes and are characterized by genes. And these chromosomes are often represented using a string, typically binary, the genes being a set of parameters. So the next component is going to be evaluation, or the fitness function. Evaluation is performed by assigning a fitness score to each individual, and the fittest or most optimal individual is noted, as is the average fitness over the population. The next step is optional, being dependent on whether the number of generations have been met or an adequate solution has been found. Otherwise, we go on to the next component, which is selection. So should the termination condition not be met, the population undergoes selection based on their fitness scores. So higher fitness increases the probability of selection for reproduction in order to pass the more optimized genes to the next generation of individuals. And those with least fitness die because they're not optimized solutions. These pairs of individuals are termed parents. The next component being crossover. So for each parent, a crossover point is chosen at random within the genes, and then these genes are exchanged according to that crossover point, and then the offspring are created and added to the population. Finally, we have mutation. So each offspring's genes are subject to mutation, which is dependent on a low random probability. It can result in some bits of the chromosome string being flipped, and mutation is for maintaining diversity within the population, which prevents premature convergence in the solution. And these are my references. Okay, thank you.